Hello and welcome to Tuesday. It's the 22nd of February 22 and the date is 22222. If you write the year as 2 digits and you ignore lead zeros, both things I would normally be upset about, but as is a matter of public record, I will make a lot of concessions for a fun mathematical holiday. And come on, 22222, that's pretty amazing. So I thought I would invite a bunch of my YouTube friends to celebrate all wonderful things about the number 2. And we're going to be raising money for WaterAid. They provide clean drinking water and sanitation services wherever they're most needed all around the world. There's a link below with more details about that. So here's how this is going to work. We're going to count our way up through the glorious powers of 2. And for each next power of 2, we'll be joined by a new YouTuber who, at some point as we go along, will share a fun fact they enjoy about the number 2. I cannot even imagine how this can possibly go wrong. So I'm technically the first one here. I'm going to ignore the 0th power because ignoring zeros is kind of a theme, sadly, to get the right date. So I'm technically 2, and the next number up will be joined with our first YouTuber is
4. Hey! Hey!
Hey! It's James Grime. James, how you doing?
I'm really well. I'm excited about Tuesday.
You look like you're the correct amount of excited for Tuesday.
Which is very excited.
All right, and I thought, if you don't mind, I will share, now that I've got an audience, my favorite thing about the number 2 at the moment. And that is that in Switzerland, trains are not allowed to have 256 axles. It's the classic power of 2 rollover error, because the number they were using in the counters on their railway system, so they would count each wheel as it hits the counter on the rails, used an 8-digit binary number to count how many wheels had gone by, and if a train had exactly 256 axles, it would register as 0 axles. And so the counter would just assume there was no train there. I actually looked up, and because I saw this online, and I suspected that can't be real. But I found the official regulation in order to avoid the danger of unintentional all-clear signals for a railway section. Because of the reset to 0 of the axles counter, a train must not have an effective total number of axles equal to 256. So 2 gives us binary, which I love, but it also gives us 256 rollover errors. What's your favorite 256 rollover error, James?
What's my favourite 256 rollover error? Well, I'm trying to give them up. I can tell you my favourite 2E fact if you like.
Oh, we tell you what, should we get some more people in and then you can give us your 2's fact?
Oh, amazing.
So we've done 2 and 4. We'll now see who comes in on 8.
8.
It's Katie Steckles.
Hello.
Katie, how you doing?
I'm okay, yeah.
Yeah.
It's a
And
good day.
you know what? Let's go wild and get the next person in as well.
16.
Hey.
Hey.
Steve Mould in a strangely portrait ratio.
Oh, no, yeah. So because I'm gonna film this for my Shorts channel as well. So I'm filming it in portrait so I can stick it on there. Yeah.
Oh my goodness. I mean, who would know more about a successful YouTube channel than Steve Mould? So anyway, now we've got a few more people in the mix. James Graham, what's your favourite fact about the number 2?
So I wanted an interesting 2 fact, and I thought, well, I'll do something classic. I thought I might do Mersenne primes. That's quite 2E. But then I thought it wasn't 2E enough. So I've decided to tell you all about double Mersenne primes for extra 2-ness. So you know your Mersenne primes, right? So Mersenne primes, they're prime numbers that are 1 less than a power of 2. So your classic Mersenne primes are like your 3, your 7, your 31, 127. These are all prime numbers, but they're 1 less than a power of 2 as well. That makes them Mersenne prime numbers. Nice thing about Mersenne prime numbers, though, this little exponent up here, this power of 2, has to be a prime as well. If it's not a prime, you don't get a Mersenne prime. Although, unfortunately, you do have to check things. So actually, if you do something like 2 to the power 11 minus 1, you get this number, 2047. It's not a prime number, you do have to check. But the next one is a prime number. So unfortunately, you do have to check, although computers are really good at checking if Mersenne numbers are prime or not. But then I thought, well, what about if we use a Mersenne prime as the exponent? It had to be a prime up there. Let's put a Mersenne prime in there, and we make a double Mersenne prime. Here are the double Mersenne primes for you. So 7, 127, and look at this one. This is 2,147,483,647. These are all prime numbers, but they use a Mersenne prime as the exponent up here. So they're double Mersenne primes, but they get really big, really fast. Look at this one. This is the next double Mersenne prime. 2 to the power 127 minus 1 is this monster. I'm not even going to say it. It's 170 million. Absolutely huge. And in fact, this is the last double Mersenne prime that we know of. Because if you keep checking, the next few Mersenne primes, they're not prime numbers. And then we get kind of stuck because these numbers become so huge that we can't even check if they're prime or not. So as far as we know, there are 4 double Mersenne primes altogether, as far as we know.
That's amazing. So we don't know if there's any more than 4.
That's it. So 4, 8.
There might just be a power of 2.
Yeah, 4 is a power of 2. Let's hope. Let's hope. Either 4 or 8. Otherwise, it just ruins the whole pattern.
Yeah, exactly. That's incredible.
This is maybe a question for Thursday, but are there any triple Mersenne primes?
Oh, that's a really good question. I'm glad you asked me that because I've got it written down on a piece of paper right here. Yeah, there is triple, there is triple Mersenne primes. Absolutely, there is.
Nothing if not over-prepared. What have you got?
Yeah, you want to see a triple Mersenne prime? All right. There's 3. That's a Mersenne prime. Let's use 3 and do it again. 2 to the power 3 gives me a 7 there. That's a double Mersenne prime. Let's use that 7. Stick it up here. 2 to the power 7 minus 1. 127. A triple Mersenne prime. Let's take that 127. Let's stick it up here. 2 to the power 127 minus 1. Is this monster that I mentioned earlier. It's that same number again. Quadruple Mersenne prime. If I could take that and stick it up here and do it again, I would have a quintuple Mersenne prime. But unfortunately, that is just so massive, we don't know if it is. If it is, fantastic. If it isn't, that sequence will never be a prime again.
That's our goal. We have to have checked that by Thursday. Right, now we need another guest, so...
32.
Hey, it's Ailey-Ann McDonald, this time from the world of TikTok. Not... Well, I guess you do YouTube as well.
I do. I'm multi-platform, yep.
Wow. I dream of the day I'm multimedia. And as well as another guest, we're also going to do another fun fact about 2. So I think, Katie Steckles, you've got something to share.
Yeah, I thought I would share my favourite fact about the number 2 in the form of a joke. Since this is a stand-up maths channel, it feels appropriate that we should at least have one. It
would be a first, I'll give you that.
Yeah. So the joke goes, infinitely many mathematicians walk into a pub, and the first one says, "I would like a pint, please." And the second one says, "I would like a half." And the third mathematician says, "I would like a quarter of a pint." And the next mathematician says, "I would like an eighth of a pint." And the bartender says, wait, just stop there, and pours 2 pints and puts them down on the bar. And, this is obviously a hilarious joke without any explanation, but it turns out that what the bartender was doing was seeing a pattern. So there's a pattern in the numbers that you get in this sequence, right? So there's a pint, there's a half, there's a quarter, there's an eighth. Each time is half as much as the previous drink. We can write this in a sort of sum thing, so we can write the sum from n equals 0 up to infinity of 1 over 2 to the power n, and that will give you that sequence of fractions. And it turns out that if you add all of those numbers together, you get exactly equal to 2, which is quite a neat little fact that you can have infinitely many things that add up to a finite thing. And I kind of like this, and you can sort of, like, if you want to sort of get your head around this a little bit, because it does seem a bit weird, you can think of it as, so you've got your first pint, which is just 1 pint on its own, and then for the other pint glass, I guess, each successive drink that gets added takes up half the remaining space. So you put in the half, you put in the quarter, and you're always taking up half the space that's left. So if you keep doing this, kind of technically you'll never actually fill up the second pint glass because you've actually always got half the space left. And it kind of means that you get closer and closer and closer to 2, but you never actually get there unless you keep going to infinity. And this is the interesting thing about it, because if you keep going to infinity, you do get exactly equal to 2. And I've done this. This is the thing that I often do. I get some beer and fill up some pint glasses with it. So here are 2 pint glasses. And there's kind of a technical definition that we have in maths for what it means for a series like this, an infinite series, to add up to a finite value. And it's essentially, no matter how close you want to get to 2, if I have enough glasses, if I have enough tiny glasses of beer, I can keep adding them until I get within that distance of 2. So no matter how small your distance between where you want to be and 2 is, I can put you in that region by giving you enough glasses of beer. So that's kind of the theory of it, and that's the definition, the technical definition of a limit. So next time you and infinity minus one of your friends go down to the pub, make sure you know your limits. That's my fact about 2.
You started and ended with a joke.
I did.
Come on.
2 jokes. for
That's
Tuesday.
definitely a new record.
Yeah, you got 2. Yeah.
It's a good point. Good point. And so, I mean, so if you don't need infinitely many of them, depending on your tolerances, if you could just have a finite number to get within any threshold.
Yeah. Yeah, I mean, it's mainly your tolerance of washing up more than anything else, because like I think the last one I had on there was 1,256, which is 2 milliliters of beer, give or take. Like beyond a certain point, you're just kind of inhaling some molecules of beer.
All right, well, let's carry on. And now for our next guest.
64! Hi, Matt.
Hey, it's Ben Sparks.
Hey, how's it going?
In the most professional looking sound studio we've had yet.
That's only because you can't see the floor of this professional sound studio, which looks unprofessional, I have to say.
Slid everything off onto the out of frame.
You know it.
Well, you were here just in time to see what Steve Mould's got about the number 2.
Yes. So actually, first I need to just set recording for my shorts channel.
You can do
Matt,
both at once.
Can you? Yes, but can you give me permission? Can you make me the host?
Oh,
And then
I can't co-host, but I can switch you to be the host.
yeah, perfect.
There. Yeah, that should. Don't mess it up. Hey, where are we?
What?
128.
Thank God. Right, no, not now. Not right. It's starting now. So it's
What's going on?
Tuesday. It's the 22nd of the 2nd, 22, which is a date that mathematicians like, which is why I've got some here on the screen. My special fact about the number 2 is, well, it's based on a sequence of numbers. The sequence goes like this: infinity, 5, 6, 3, 3, 3, 3, 3, 3. Just goes 3 forever after that. It's the number of platonic solids in different dimensions. So in 3 dimensions, you might know there's the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. That's 5. There are 6 in 4 dimensions, and there are 3 platonic solids in every dimension higher than that. But in 2 dimensions, there are infinitely many. It's just the regular polygons. That's my interesting fact about the number 2.
Isn't this a YouTube Shorts with a very strict time limit, Steve?
It is, yeah.
Oh, what? So we're going to get... Oh, I've got an idea. Follow me to number file 2.
Oh, link in the description.
512. Where is everyone? Hello? Hello? Matt, this is why you haven't got 1 million subscribers yet. Honestly.
I'm here for 1024. This call would be more fun if there was 2 of us here. Yeah, I'm just gonna leave.
Hi, hello, 2048, hello? Anyone there? I assume it's recording. Did you know that a 2% or better accuracy for electronic components is a luxury? The majority of them are not even accurate to 2 digits. For example, resistors, 5% accuracy is most common, and for capacitors, they can be as bad as 10 to 20% off. That's what makes analog circuit design for precision devices so challenging. The majority of an engineer's effort goes towards managing these inaccuracies. Makes you really appreciate the super incredible accuracy of some instruments like the Space Weber James Telescope. And you thought engineers could easily put 2 and 2 together to get 4, but no! The temperature changes, wind blows over your circuits, and suddenly 2 plus 2 becomes 4.1. Hello? I'm talking to myself here.
$4,096. Where is everyone? Okay, never mind. Gonna tell you my fact anyway.
Say you have two particles and they each have two states that they can be in. Call them heads and tails. For quantum entanglement to happen between these two particles, what you need is to fulfill two criteria. One is that the state of the particles always depend on each other. For example, if I make sure that they're always opposite to each other, then the state of the first particle is tails if the second is heads, and it's heads if the second is tails. And the second criteria is that nothing has observed which of the two states these two particles are in. Not a person, and not even other things like particles of light. So as long as those two criteria are met, that the particles depend on each other in some way, and that nothing and no one has measured them, then the two particles are entangled.
Hello, I'm 8192, and there is, by the looks of it, no one else here. Oh, right. I'm going to go train spotting then. Hello, I'm Jeff Marshall. Follow my channel. I do transport, travel, and the occasional train video, and we can't have Tuesday without the most amazing 222 train. That is the Class 222 here on East Midlands Railway, and it's unit number 2 of the Class 222 family. All the 2s in the railway world. Fantastic.
$16,384. Guys? Okay. 2 is the highest number of dimensions that a random walk will loop back on itself with probability approaching 1. This means that if you leave it for a long enough time, it's pretty much guaranteed that the random walk will return to its place of origin. This isn't true for 3 dimensions or higher, however. While there is some probability that the random walk will return to its place of origin, it's not guaranteed.
32,768. Well, did you know that the laser cutter, which is becoming so popular in the hobbyist world, is actually considered to be a 2-axis robot? Let me show you. Just as the name implies, we're going to be using a laser to cut our way through the workpiece. But we definitely don't want to have to move the whole laser tube around. So the way we do that is we take the laser tube and place it here in the back, and then we use a series of mirrors. It's pretty dark in there, so that one's hard to see, but there's one here and one here. Inside of here, we've got one more lens, which is going to focus that laser beam at just the right height. Of course, we also need to move the laser beam around. And this is where our 2-axis coordinate system comes in. We've got guide rails here on the side, which keep this axis moving in a straight line. And there's a computer-controlled motor, which will pull and push it along this axis, giving us the y direction. And just like the Cartesian coordinate system you learned in school, there's also an x, and that can be controlled by the motor moving on this axis. And same thing, we've got a guide rail right here. Now that we can position the laser wherever we want, we just need a computer program which can take our shape and turn that into coordinate positions for the laser to move to. At the end of the day, it allows us to make very complex parts without much effort. How cool is that?
$65,536. Oh, wait a second. Where is everyone? I was expecting a lot more company. This is kind of strange. Well, like everyone else, I'm here to celebrate Tuesday, and the power of 2 that I get to celebrate is 65,536. Now, why do I like this power of 2 so very much? Well, it seems very fitting as a particular power of 2 to talk about on Tuesday, because 65,536 is 2 to the power of 16. But 16 is a power of 2, so therefore I can write this as 2 to the power of 16, but I can also write it as 2 to the power of, well, 16 is 2 to the power of 4, so I can write it as 2 to the power of 4, but 4 is also a power of 2, it's 2 squared, so therefore I can write this as 2 to the power of 2 to the power of 2 to the power of 2. I think I said the right number of 2's there. It's very confusing on Tuesday. So not only can you write 65,536 as this kind of tower of 2's, it also has a really cool property that for me is incredibly counterintuitive and really hard to guess, but you can see it right by looking at the number, just by paying attention to its digits. I wonder if you can spot what is unusual about 65,536 as a power of 2. Have a look at the digits. 6, 5, 5, 3, and 6. 65,536 is the only known power of 2 for whom none of its digits are powers of 2. Did you get that? Let me see if I can explain this. The powers of 2 that can be digits are, of course, 1, 2, 4, and 8. And there are none of these digits in 65,536. But this is the only time that we know about that it happens. We have calculated some really large powers of 2, but none of them that we have found, apart from 65,536, has no powers of 2 in its digits, which to me is astonishing because the powers of 2 are really sort of predictable in a way. If you want to try and work out what the digits are, say for example, let's think about the last 2 digits, the tens and the units, right? If we just focus on those, we start at 1, and then we get to 2, and then we get to 4, and then we get to 8. When we cross over into double digits, we then get 16, 32, 64. And at this point here, well, okay, we go into 3 digits, but let's first focus on the tens and the units for a second. It'd be 128. So we're going to get 28 as our tens and our units. After 28, it's going to be, well, I can just double that. It's going to be 56. The next one after that, if I just think about 56, I don't have to worry about the hundreds and the thousands. That's going to be 112, so I'm just going to put down 12. We're back into 2 digits again, so 12 to 24 to 48 to 96. 96, when you double that, is 192, so 92. 92, when you double that, that's 184, so 84. 84 doubled, that's 168. Double this, okay, we've got to carry the 1 here, so it's going to be 16 plus 120, so 136. Double that, 72. 144. 88 when we double that. We're almost at the end here. Double 88 is 176. Doubling that is 152. And this is the important point, because now when you double 52, you get 104. So you're at 0, 4. So now the cycle that we've just sort of created will begin. I'm back here at this point, and now you're just going to get 8, 16, 32. So there is this predictability to those last digits on the ends of all of our powers of 2. These are just going to cycle around and around and around. But despite that predictability, we still have not found any other powers of 2 which don't have powers of 2 in the digits. And I think that's cute. So 65,536. Happy Tuesday, everyone. Still no one here joining me, which is slightly sad, but hopefully you all get to celebrate this day in a way that fits you. Bye!
131,072! You're all on mute? Hello, anyone? You're gonna miss my interesting fact about the number 2. Okay, how about this? 2 is greater than the number of people in this video call. Prove me wrong. No takers. Okay, how about this? Little known fact. Did you know that 2 is actually the first number ever invented, because if you only have one thing, you don't need numbers? And so 2 was invented in around 3000 BC by... No one's gonna call me out on making this up? Okay, you're really not here. That means I can share my most secret fact about 2, and no one can scoop me on publishing. Okay. So normal space of any number of dimensions, chiral things come in 2s, chiral pairs, a thing and its mirror image that's different from the original. And there are 2 possible chirality statuses, either you're chiral or you're not. You can also be metachiral, but that's still chiral. Which you might think is obvious because mirrors make pairs of things, but little known fact that maybe I also made up. But this time it's true, because making up true things is what math is. That in space-time, like music or dance or probably everything, chiral things come in 4s, not 2s, because mirroring in space and in time are different things. Also, sometimes something can be chiral in space but achiral in time, or vice versa, for a total of 4 potential chirality statuses. And in theory, if you have space, time, something else, I mean, I'm not really up to date in what else there is besides space and time these days, but I can imagine how it would work mathematically. And the symmetries involved would include even higher order chirality statuses, so that in normal everyday space we're used to having exactly 2 chirality statuses, and that chiral things come in pairs, is pretty special. Thanks, 2!
Hey everybody, 262,144. Oh, well, I guess they were too busy. 2 hands, 2 feet, 2 lungs, 2 eyes, 2 kidneys, 2 bladders. But when it comes to the really top-tier important organs, we only get 1. Although I guess you could argue that brains have 2 hemispheres and hearts have 2 ventricles, 2 arteries, and so on. And while I do love talking about organs, I want to tell you about evolution, because you might have heard that we differ from chimps by less than 2% of our DNA, and that's true, we are very closely related, but we differ from the other great apes in a very important way. We have 2 fewer chromosomes. We have 23 pairs, that's 46, and they have 24, that's 48. See, my maths skills are pretty much on a par with Matt's. So what happened? Evolution tells us that we have a fairly recent common ancestor, so how do we have 1 fewer pair of chromosomes? We can't have lost all that genetic material, there's too much contained therein that would have been incompatible with life. So what we can do is line up human chromosomes next to chimps, and actually they match up very nicely. You can see that they're incredibly similar, except for one of the chromosomes, which is a jumbo human chromosome, but which actually matches up to 2 of the chimp chromosomes. So what happened is, at some point in history, those 2 chromosomes merged and formed this one jumbo chromosome. And why is this important? It's because it marks a fork in our evolutionary history where we were no longer genetically compatible. And that chromosome is chromosome 2. Sorry, that's just my pager going off. 2222. I'm sure it's nothing important.
524,288. Fine. Didn't want to talk to any of you anyway. My fun fact is not about the number 2, but instead the number 22. Suppose you have a pizza, and you're allowed to make 6 cuts. What is the maximum number of slices you can produce? As you may have guessed, it's 22, and here's why. Let's consider the general case of cutting a pizza with n cuts. By considering cases for small values of n, we can spot a pattern. Looking at the pattern in the table, we can see that the value at step n is just the previous value plus n. So the answer for 6 cuts is going to be a maximum of 22 pieces of pizza. We can also write down a recursion formula that follows the same pattern, and using Gauss's summation of the first n natural numbers, we can get the following. If f is the function which outputs the maximum number of pieces for n cuts, then this is equal to a half n times n plus 1 plus a final 1. This drawing shows one possible example of how you can use 6 cuts to form 22 slices of pizza. For the full details of the maths behind this formula, check out the follow-up video on my own channel, Tom Rocks Maths, and in the meantime, enjoy this footage of me trying to cut a pizza into 22 slices.
Two raised to the 20th power, that's 1,048,576. Where did you go? I was supposed to be here. I did my... Oh, okay. So we have an abandoned channel on our hands. I've always wanted a second Smarter Everyday 2. I'll be right back. Hey, it's me, Destin. Welcome to Smarter Every Tuesday. I know that was hard for me to say, but I've always wanted a second channel, and since Matt abandoned this one, was it Stand Up Maths? We'll have to change the title down there. Anyway, on the first episode of Smarter Every Tuesday, sorry, gotta get that right, I want to explain to you what the history of Tuesday is. Now, it seems like, you've got Monday and then Tuesday, so why isn't Wednesday Threesday? Well, Tuesday doesn't mean 2 as in the number 2. It actually has to do with this guy right here. This is from the Old English word Tuesdag, which literally means Tuesday, as in T-I-W. This is like an old god of war or something like that. I'm supposed to know more about that here on Smarter Every Tuesday, but we'll get there. But I'm not really into the war thing. I'm more of a peaceful kind of guy. So for me, I thought it was interesting that we named this after this god of war. And interestingly, this is documented in ISO 8601. This is an international standard, and this is what dictates what days of the week are called. Anyway, let's get away from the war thing. I'm more of a do unto others as you would have them do unto you kind of person. And the interesting thing about that is you can't really have a do unto others unless you have 2 people. So the 2 people, like being nice to each other, has a lot to do with how the golden rule works. So anyway.
Hey! Destin, this is my channel.
Well, this is not your channel. You abandoned it. So it's clearly Smarter Every Tuesday now. And I mean, this is the first episode. You know the deal.
I did not abandon it. We're just all over on number file 2. Here, hang on. Let me share my screen. I'll show you.
Okay. I mean, but I showed up and nobody was... Whoa!
What's going on?
Oh, no, I think... I've opened a double recursion wall!
My God, it's full of twos.
Twos all the way down.
Sometimes a double recursion visual gag can spiral out of control, and when that happens it can take the whole universe with it, and only folks who are lucky enough to be on vacation and making an extra dimensional journey at the time notice it, and it's their job to read the credits. Thanks to Eugenie von Tunzelmann, who was convinced by Matt to render this whole thing, and to all the YouTubers who were talked into doing what was meant to be a simple Tuesday video. Links to all of them are down in the description, although they are now lost in an infinite recursion loop until someone resets the universe. Again.
Can you please just turn the universe off and on again?
I did it last time. All that remains now is to donate to WaterAid and wait patiently for Threesday Thursday.
Tom? Maybe try Alt F2 squared.
Every time.